Okay, in this section we're going to be dealing with rational functions and their graphs. Now, I'm only going to go over part of it today. The other part I will cover in class on Tuesday. Mainly we'll talk about what rational functions are. We're going to find the domain of a rational function. Also, we'll look at what a vertical asymptote is and how to locate a vertical asymptote. We'll also talk about the hole in the graph, how to graph a rational function with a hole in it. And then we'll talk about horizontal asymptotes, what it is, and how to locate a horizontal asymptote. Now, Tuesday when I come back, I'll be talking about the 7-step procedure for graphing a rational function, and then go into what a slant asymptote is and how to find the slant asymptote. Okay, so let's talk about what rational functions are. We did talk about rational equations and how to solve rational equations. So let's look at what rational functions are. Now, rational functions, by definition, are going to be quotients of polynomial functions. Expressed as this. Let me have some more space here. It's going to be expressed as f of x equaling to p of x divided by q of x. And that is going to be where your denominator, q of x, is not equal to 0. Okay? So, the denominator cannot be equal to 0 here in this case. And when you're finding the domain, you're always going to set your denominator equal to 0. So here, the domain of any rational function is the set of all. Now I'm going to underline this word real numbers, because in this case we're dealing with real numbers, except the values that would make the denominator zero. Because as we know, we cannot divide by 0. That is definitely undefined. Okay? We did talk about this in one of the earlier sections in chapter 2. So let's look at some examples here to bring you up to speed. So here we're going to find the domain. Let's start up with this rational function. F of x is equal to x squared minus 25, all divided by x minus 5. Okay? So now in this case here, the denominator is x minus 5. Okay? We want to find out what values of x where I'm going to get a 0 in the denominator, so I take that x minus 5, which is my denominator, set it equal to 0, and solve for x. So, for x minus 5 equal to 0, that would mean x is equal to 5. So here at x equals 5, I'm going to get a 0 in this denominator, okay? Now, if you want to, you could draw a number line to help you write the interval notation for that. Because I'm pretty much sure that in the homework they're going to ask for the interval notation. We know at 5, you're going to get a 0 in the denominator. Any x value less than -5 would work, and any x value greater than 5 would work. So, in interval notation, the domain would be this. Going from left to right would be from -infinity up to 5, or from 5 to infinity. Now, if they want the set builder notation, it will be this: the set of all x such that x is not equal to 5. Okay? That means all real numbers except 5. Okay. That's part A of example 1. Now part B. To say g of x is equal to x divided by x squared minus 25. And I want to find the domain. Here I've got x squared minus 25 in the denominator, so here I'm going to take that x squared minus 25 and set that equal to 0. And solve for x. So in this case here, I can go ahead and add 25 on both sides to get x squared by itself. So here x squared is equal to positive 25. And then the opposite of squaring something would be to take its square root on both sides. So that means I'm going to have x is equal to, and I forgot the plus or minus, don't forget that. So here you got x is equal to plus or minus 5. Okay. I'm going and work this out so I can include the plus or minus in this problem. Okay, so at x equals 5 and at x equals -5, we are going to have a 0 in the denominator. So in this case here, if I draw this on a number line, so I know at -5 and at 5, I'm going to have issues here because I have zeros in the denominator at those two numbers here. Any x value less than -5 would work. Any x value in between -5 and 5 would work, and any x value bigger than 5 would work as well. So, here's the domain in interval notation. Let me bring this up a bit. That's going to be from -infinity to -5, or -5 to 5, or 5 to infinity. That will be the domain in set builder notation, in interval notation. Now set builder notation is just this: a set of all x such that x is not equal to 5, or x is not equal to -5. Interval notation, then set builder notation. And let's look at one more of these domain type problems here. In this case, let's say h of x is equal to x plus 5 divided by x squared plus 25. And here I want to find the domain of that rational function. Well, I take my denominator of x squared plus 25, we'll set that to be equal to 0, and solve for x. So, to get x squared by itself, I need to subtract 25. So here you get x squared is equal to negative 25. And then if I take the square root on both sides, I don't want to forget that plus or minus symbol like I did in the last example, I have x is equal to plus or minus. If I take the square root of 25, that would be 5. But the square root of a negative 1, that's I. So here I got 5i and negative 5i. Unfortunately, I'm not going to be able, those are a pair of imaginary numbers. We're dealing with real numbers for the domain. Okay? As you remember, I did say that the domain of a rational function is a set of all real numbers. These are a pair of imaginary numbers. And if you look at your denominator, it's never going to be negative because you're squaring it and adding 25 to it. So, the domain in interval notation would be this, all real numbers, negative infinity to infinity. And of course, the set builder notation for that would be the set of all x such that x is a real number. Because with the x squared plus 25 in the denominator, your denominator will never be 0. Because you're squaring it and you're adding 25 to it. So that's how we find the domain of any rational function. Okay? So this is kind of a review from another section that I talked about this concept. Okay, next we'll look at a vertical asymptote. That concept of finding the domain, setting the denominator equal to 0, that's the way of finding the vertical asymptote of a rational function. And it's going to be the line called x equals a for the function f of x. If f of x increases or decreases without that. Draw an illustration of what a vertical asymptote would look like for a graph of some rational function. Okay. And usually the vertical asymptote will be a vertical dotted line, something like this. Here it is. That's what the vertical asymptote would look like. And if I have a graph of a function y equal f of x, that graph will approach that vertical asymptote, but it will never touch the vertical asymptote. Okay? It'll approach the vertical asymptote, but will never touch it. Okay? That's what we mean by a vertical asymptote. It's just a vertical dotted line. And it's usually going to be where it's going to be going through the x value where your rational function would be undefined. Okay? Now, let's talk about how to locate a vertical asymptote. So you're going to be locating vertical asymptotes. if f of x equals to some p of x over q of x, and p of x and q of x are polynomial functions, by the way, I forgot to mention that. Which is a rational function where p of x and q of x have no common factors, and a is a zero q of x, and the q of x is going to be your denominator, then x equals a is the vertical asymptote. Now I'm going to give you a minute or two to write all this down because this is kind of lengthy here. Okay? What that means here is this: you'll take your denominator, set it equal to 0. Also, you want to make sure that p of x and q of x have no common factors. If there are common factors, you want to go ahead and divide out those common factors here. Okay? And then find out what your vertical asymptote will be by setting your denominator equal to 0. And then you'll know what they are. Okay, so in this example here, well, in these few examples here, under example 2, we're going to find the vertical asymptote. If any. That is, if there is one. Okay? So now in part A, let's say we've got f of x is equal to x divided by x squared minus 1. F of x is equal to x over x squared minus 1. And he'll want to find out what that vertical asymptote is, if there is one. Well, what I'm going to do here is factor the denominator of x squared minus 1, because that's a difference of two perfect squares. X squared is a perfect square, and 1 is a perfect square. So in this case here, I can factor x squared minus 1 as this: x and x, and then 1 and the 1. 1 has to be plus, the other one has to be minus. So the x plus 1 times x minus 1 in the denominator. The numerator, I can't factor that. It's already in simplest form. And I don't have any common factors to divide out here. So I can go ahead and set the denominator of x plus 1 times x minus 1 to be equal to 0, and solve for x. So for the x, I have x plus 1 equals 0, and x minus 1 equal to 0. Set each binomial factor equal to 0. Now I can solve for x. X plus 1 equals 0 means x is equal to negative 1. And then for the x minus 1 equal to 0, I got x is equal to 1. So these are my two vertical asymptotes here. X equal negative 1 and x is equal to 1. Those will be the two vertical dotted lines that will be crossing the x-axis at 1 and at negative 1. Okay. So that's part A. Part B. Let's say that g of x is equal to x minus 1 divided by x squared minus 1. and I want to find the vertical asymptote for that, if there is one. Okay, let's see if I can factor the numerator and the denominator out. Well, x minus 1 is already simplified. Can't do anything with that. The x squared minus 1, I can factor that out into two binomials just like I did with part A. X squared minus 1 is this right here, x plus 1 times x minus 1. Now notice here, I have a common factor in the numerator and the denominator. I can divide that out. I can divide out the x minus 1. And here we'll have a 1 in the numerator and an x plus 1 in the denominator. So I'm going to be left with g of x equaling to 1 over x plus 1. Okay? So here I have to get rid of my common factors before I can determine what's my vertical asymptote is going to be. And in this case, I can take that x plus 1, set it equal to 0, and solve for x. And then if I subtract 1, I'm going to get x is equal to negative 1. So in this case, I only have one vertical asymptote, and that would be x equal negative 1. So here I got one vertical asymptote, and that's at x equal negative 1. Now part C. Here we got h of x is equal to x minus 1 times x squared plus 1. X minus 1 divided by x squared plus 1. X minus 1 divided by x squared plus 1. Now, in this case here, I need to take my denominator of x squared plus 1. Now, I can't factor the sum of two squares. I can only factor the differences of two squares. So, that x squared plus 1, I just have to set that equal to 0 and solve for x. Now, if I subtract 1, this will be x squared is equal to negative 1. But if I take the square root on both sides, because that's the opposite of squaring something, the square root of negative 1 would be I. Those are a pair of imaginary numbers here, I and negative I. In this case here, I cannot. Those are not real numbers, those are imaginary numbers here. And in this case, I can't graph I and negative I on a coordinate plane. And if you look at this, if I square this and add 1 to it, I'm never going to get 0 in the denominator. The denominator will never be 0 because of the square, and I'm adding 1 to it. So this rational function will have no vertical asymptotes. No vertical asymptotes. Okay. So that's how we locate vertical asymptotes for rational functions here. Okay, now if we go back to part B, where I had to divide out common factors. Anytime you have to divide out common factors like I did right here in part B, you're going to have something called the hole in the graph. And that's the next thing I want to talk about here, hole in the graph. A hole in the graph occurs when your common factors divide out. So when your common factors divide out, that means you have a hole in the graph. Like in this example here that I'm going to give you. Here we got f of x is equal to x squared minus 4 all divided by x minus 2. Now, in this particular case here, the denominator is x minus 2. What would be the restriction here? If you do x minus 2, set it equal to 0, that would mean x will have to be equal to 2. At x equals 2, I will have a 0 in the denominator, okay? Now I'm going to factor the x squared minus 4 because that is a difference of 2 perfect squares here. So in this case here, x squared will be x and x. 2 times itself will give you 4. The middle term is a minus, so one has to be plus, the other one has to be minus. So you got x plus 2 times x minus 2, all divided by x minus 2. Now I'm going to bring down the restriction that x can't be equal to 2. And here I can divide out the x minus 2's here. That tells me at x equal 2, I'm going to have a hole in the graph. So my function simplified would be x is equal to, f of x is equal to x plus 2, with the restriction that x is not equal to 2. Okay, and off to the side, I'm going to create a table of values here. I'm going to say from negative 2, negative 1, 0, 1, 2, and 3. But I'm going to keep in mind at x equals 2, this is where I will have what they call the hole in the graph. So when I plot this, I will have to plot an empty circle at that ordered pair when x is equal to 2. So like this, let's say x equals negative 2. Well, here negative 2 plus 2, that'd be 0. But x is negative 1. Negative 1 plus 2 would be 1. But x is 0. 0 plus 2 is 2. But x is 1. 1 plus 2 will be 3. Now for x is 2. 2 plus 2 will be 4. So at the ordered pair 2, 4, that's where I will have a hole in the graph. And then for x equal 3, 3 plus 2 will be 5. Okay, so now I'm going to go ahead and plot all of this on a coordinate plane. Okay. I'm going to go ahead and break this up. There's my coordinate grid. And then I'm going to plot negative 2, 0. Will be to the left 2 and on the x-axis. Negative 1, 1 will be to the left 1 and up 1. 0, 2 will be on the y-axis. 1, 3 will be to the right 1 and up 3. 2, 4 will be to the right 2 and up 4. But at 2, 4, that's where I will place an empty circle. That's where the hole in the graph will be at. And then 3, 5 will be to the right 3 and up 5. Now if I connect those points, now I'm not going to draw the line through that particular hole. Okay. So here is the graph of that particular function, f of x equal to x squared minus 4 divided by x minus 2. Okay, so here it's simplified to this, but the restriction there will be x is equal to, is not equal to 2. Because at x equals 2, the order pair 2, 4 will have the hole in the graph. Okay, so that's how you graph a function with a hole in that graph. Okay, now let's talk about a horizontal asymptote. Since we have a vertical asymptote, we also have a horizontal asymptote. That's going to be the line y is equal to b for the function f of x if f of x approaches some constant b as x increases or decreases without bound. And pretty much I'm going to do one illustration of what a horizontal asymptote will look like on a coordinate plane. So the horizontal asymptote will be a horizontal dotted line going straight across, like this. So this will represent my horizontal asymptote. It crosses the y-axis at some numerical value b. And here's the graph of y equal f of x. It can approach the horizontal asymptote and not necessarily touch it. But here, this can cross the horizontal asymptote. And it all depends upon what your rational function is, okay? Your graph can possibly cross that horizontal asymptote. But for the vertical asymptote, we know the graph can never cross that vertical asymptote. Okay? And now, let's take a look at how we can locate a horizontal asymptote. And this one's going to be a lot different from locating a vertical asymptote. So here I'm going to let f of x equal to, now I'm going to write this out in the general form. The numerator is going to be having a's in it and n's. A sub n, x to the n plus a sub n minus 1, x to the n minus 1, and so on all the way down to a sub 1, x plus a sub 0. That's divided by your b sub m, x to the m, b sub m minus 1, x to the m minus 1, all the way down to b sub 1, x plus a sub 0. The only restrictions there will be your a sub n and b sub m. Those are your leading coefficients in the numerator, and the denominator can't be equal to 0. I apologize for that. Now, I'm letting n be the degree or the highest exponent of the numerator. Back in section 3.2, we did talk about the degree, which is the highest exponent of a polynomial function. So n is the degree of the numerator. Your m is the degree of the denominator. So here's n and here's m. You are going to compare those two, and that will tell you what type of horizontal asymptote you will have if there is one. Okay? Now, if your n is less than m. If the highest exponent in the numerator is less than the highest exponent in the denominator, that means the x-axis or the equation y equals 0 is the horizontal asymptote. Now the second case is where n is equal to m. If the highest exponent in the numerator equals the highest exponent in the denominator, then you're going to look at your leading coefficients to get your horizontal asymptote. That would mean the line y equals a sub m divided by b sub m. Highest, the leading coefficient in the numerator, leading coefficient in the denominator. Okay? And we should already know what a leading coefficient is. Leading coefficient is the coefficient of the variable to the highest power in the numerator and in the denominator. In the third case, if your n is greater than m, if the highest exponent in the numerator is greater than the highest exponent in the denominator, then the graph of f of x has no horizontal asymptote. It will have no horizontal asymptote here. Okay, so for now, let's look at a few examples here in example 3. Here we're going to find the horizontal asymptote if any. So let's say we got f of x is equal to 9x squared divided by 3x squared plus 1. And he'll want to find out what the horizontal asymptote is, if there is one. Well, we need to identify the n and the m. The n is the highest exponent in the numerator. Is the numerator, the highest exponent in that numerator will be your 2. The m is the highest exponent in the denominator. That's going to be 2. Compare n and m. If you compare those two, you're going to see that n and m are equal to each other. So that means we have to look at our leading coefficient in the numerator and the denominator, a sub m divided by b sub m. A sub n, well, a sub n, I need to make a correction here. This is a sub n, not a sub m. Okay. So this is a sub n right here. A sub n is the leading coefficient in the numerator. In this case, it's going to be 9. B sub m is the leading coefficient in the denominator. That would be 3. 9 divided by 3 is 3. So the equation y equals 3 is the horizontal asymptote for that rational function. Part B. G of x is equal to 9x divided by 3x squared plus 1. And I want to find out what that horizontal asymptote would be. Let's identify the n and the m. The n is the highest exponent in the numerator. Well, the highest exponent there for the x is the understood 1. So your n is going to be 1. The m is the highest exponent in the denominator. That's your 2. Now you're going to compare n with m. Here you see n is less than m. 1 is less than 2. So n is less than m. That would mean if n is less than m, then your x-axis or the equation would just say y equals 0 is your horizontal asymptote. And then finally part C, h of x is equal to 9x cubed divided by 3x squared plus 1. Identify the n and the m. The n is the highest exponent in the numerator. That will be 3. Your m is the highest exponent in the denominator. That's going to be 2. Now, if you compare your n with the m, n is greater than m. 3 is greater than 2. And since n is greater than m, that means that h of x, that function will have no horizontal asymptote. Okay, there's no horizontal asymptote there. Okay, so that's how we locate a horizontal asymptote. It's a little bit more complicated than it is finding the vertical asymptotes. Okay, and I'm going to end this video right here. Okay, so when I return on Tuesday, we will pick up with a procedure for graphing a rational function. We're going to take all of this that I showed you and show you how to graph a rational function using the 7-step procedure. And do feel free to email me or call me if you have any questions about this.